Now that we know how to name and draw alkanes, let's talk about the physical properties of alkanes. Let's start with the boiling point and the melting point. Now you have to remember that boiling points and melting points of alkanes increase with the number of carbon atoms. This is due to the increase in surface area. So the increase in surface area leads to a stronger intermolecular forces, particularly the van der Waals forces. So this would require higher temperature to break the bonds. Recall that intermolecular forces are the forces of attraction or repulsion which act between neighboring particles. So this is how they react when there's an atom or molecule near them. So if you're going to consider this example, methane and octane, methane's boiling point is negative 161.5 degrees Celsius. Octane's boiling point is 125.6 degrees Celsius. For the melting point, same trend follows. Negative 182 degrees Celsius for melting point and negative 57 degrees Celsius for octane's melting point. Branching in alkanes lowers the boiling point. So more branching, less surface contact between molecules. This branching weakens the intermolecular forces. Consider the example isobutane and butane. Okay, isobutane's boiling point is negative 159.42 degrees Celsius. Butane's boiling point is negative zero point 0.5. Here is a linear chain. Isobutane is a branched chain. So it's the same. You have 1, 2, 3, 4 carbon atoms. You have 1, 2, 3, 4. Next would be the solubility and density. Now remember, alkanes or most organic compounds are non-polar molecules, except when they have polar functional groups, which we will discuss in a while. So alkanes are non-polar, meaning they do not dissolve in polar solvents like water. Remember the general rule, like dissolves like. Alkanes are typically less dense than water. That's why here in the example, when you mix hexane and water, after some time, the hexane will float. Now let's have the state of matter. For smaller alkanes or alkanes that have 1 to 4 carbon atoms, they are usually gases. For medium alkanes, 5 carbon to 17 carbon atoms, they are typically liquids. For long chain alkanes, 18 carbons and above, they are solid. So if you're going to refer to this table, you can see here the molecular formula, number of carbon atoms, melting point, boiling point density, and the physical state. Now let's talk about the functional groups. Recall from the biochemistry class that functional groups are groups of atoms within molecules that determine the chemical properties of those molecules. Think of functional groups as accessories, right? When you wear accessories, you are, let's say, 3 points more confident than before, right? Okay, so we have a lot of functional groups, which we will not discuss, okay? So we're just going to pick some of them, and here are the functional groups that we're going to study. We have the alkenes, alkynes, arenes, alcohols, ethers, alkyl halides, and the thiols. So alkenes, they have double bonds. Alkynes, they have triple bonds. Arenes, they have the benzene ring, if you remember. It has the conjugated system, right? Alcohols, they contain the hydroxyl group OH, ethers, ROR. Then you will see here the alkyl halides are XX. Here is a halogen atom. So the fluorine, chlorine, bromine, iodine, and the thiols, they have the sulfhydryl. So in this slide, you will see the importance and biological functions of these functional groups. So alkenes are important as building blocks in organic synthesis. They are used to create a variety of chemicals, including plastics. So their double bonds allow for unique reactivity. So it enables them to undergo addition reactions. Okay. For their biological functions, some alkenes are found in natural products, such as terpenes, which have roles in fragrance. Alkenes, they are used in various industrial applications, including welding. So their triple bonds make them highly reactive, allowing them to participate in diverse chemical reactions, particularly polymerization. For their biological function, they can serve as intermediate in biosynthetic pathways. Arenes, if you remember, they are very stable because of the delocalized pi electrons. So their ability to undergo substitution reactions allows for the introduction of various functional groups. For their biological functions, many natural compounds such as hormones and vitamins contain aromatic structures. So I hope you remember the structures that we discussed in biochemistry. For alcohols, of course, we know them as solvents, disinfectants, and production of fuels, for example, ethanol. So their OH group enables them to engage in hydrogen bonding, which of course affects their boiling point, solubility, and reactivity. For their biological functions, alcohol play crucial roles in metabolism. And if you remember, they're also involved in the synthesis of lipids and carbohydrates. Ethers are commonly used as solvents in organic reactions due to their low reactivity and ability to dissolve wide range of compounds. So their structure allows them to act as good solvents for nonpolar and polar substances. For their biological role, some ethers are important in biological signaling. So, for example, in lipids, and they can also act as anesthetics. Alkyl halides are important in organic synthesis and can undergo nucleophilic substitution and elimination reactions. So they are very valuable intermediates. So I think we're going to discuss that soon. I hope so. For their biological functions, some alkyl halides can be bioactive and they play roles in various biochemical pathways. In the industry, they are also used in pharmaceuticals, agrochemicals, and other industrial chemicals. For thiols, thiols are important in organic synthesis and can form disulfide bonds, which is another functional group. So they are involved in redox reaction and serve as reducing agents in various chemical processes. Thiols are very important in protein structure and function. So they also play a role in antioxidant activity and metabolic pathways. Okay, so more importantly, let's discuss polarity. When we say polarity, it refers again to the distribution of electrical charge around atoms. So if you have an even distribution of electrical charge, they are polar. Okay, if you have even distribution of electrons, they are nonpolar. Okay, consider this Cl2. Cl2 is nonpolar because they have the same electronegativity. Okay, so there's no uneven distribution of electrons. Okay, recall that electronegativity is the tendency of an atom to attract the bonding electrons. So if one is more electronegative, of course, it will attract the electrons in the bond, making it more negative. So consider this example, HCl or hydrochloric acid. Cl here is more electronegative. So if we're going to look at the electrons, they are closer to Cl. And if electrons are closer to you will become partially negative, which makes hydrogen here partially positive. Okay, so there is an uneven distribution of electrons. That's what we meant by polar. So this table shows the electronegativity table. Hydrogen is 2.1, chlorine is 3.0. If you subtract 3.0 from 2.1, you will get 0 0.9. 0 0.9 is here, moderately polar covalent. We will not really discuss this electronegativity table, but I just really want to show them to you. So let's start with alkenes. Alkenes are nonpolar because they are mainly composed of carbon and hydrogen, which have very similar electronegativities. Also, the C double bond C is symmetrical, so there's no significant charge separation. For alkynes, like alkenes, they are also composed of carbon and hydrogen, so the C triple bond C is linear and symmetric, leading to an even distribution of electron density. So again, there's no significant charge separation. For arenes such as benzene, it has a ring structure with the localized pi electrons. Again, if you recall, these are electrons that are shared evenly over the entire structure. So this delocalization makes the molecule highly stable and non-polar. despite the presence of the double bonds within the ring. Alcohols are polar because the OH is highly polar, or the hydroxyl groups are polar. Okay, so there's a large difference in electronegativity between oxygen and hydrogen. Oxygen is much more electronegative, pulling the shared electrons closer to itself. Ethers contain an oxygen atom that is more electronegative than carbon or hydrogen, so giving it some polarity. However, because the oxygen is between two R groups or alkyl groups, remember it's ROR, right? The polarity is reduced compared to alcohols. For alkyl halides, these are polar. Okay, so remember halogens are fluorine, chlorine, bromine, iodine. They are much more electronegative than carbon. So this would create a strong dipole when they are bonded to a carbon atom. So the halogen, again, pulls electron density toward itself, making the carbon partially positive. Lastly, thiols, they are slightly polar. Okay, so the sulfur atom in thiols is more electronegative than hydrogen, but less electronegative than oxygen in alcohols. So this creates a weaker dipole compared to hydroxyl groups, resulting in a slightly polar bond. Thiols have less hydrogen bonding potential compared to alcohols. So now, why do polarity matter? Two reasons. Number one is solubility. So remember we discussed the fundamental rule in chemistry and biology, like dissolves like. Polar substances dissolve in polar solvents. Non-polar substances dissolve in non-polar solvents. And number two is reactivity. So polarity influences how molecules react. Polar molecules are more likely to participate in reactions with nucleophiles or electrophiles, while nonpolar molecules are less reactive under standard conditions. So this is solubility, which we discussed a while ago.